Power series. This section is most useful, and you will find it so in differential equations when you get to that particular chapter and section. Here, we want to be able to describe a function based on a power series. Now, this section is only an introduction to power series, and so you won't get the full gist of it until I believe it's not the next section, but the section after this, where we can utilize the importance of being able to take any function and represent that function using a power series. Now, there's some disclaimers, that is, that say any function, there are certain functions that it might not be able to be expressed as a power series if there are some discontinuities. But for the most part, we can take most typical functions and represent them with a power series. And then from there, instead of focusing on the function, you focus on the power series. So whatever you would do to the function, you do that same thing to the power series. Thus, you're able to solve equations, differential equations. You can integrate a power series like you would a function. You can take the derivative of a power series like you would a function. So the introduction. What's the power series? The power series is defined, and to be honest with you, it's a geometric series, ideally. Now, x is any variable, so if x is a number between 0 and 1, then we have a geometric series. So a power series here is an infinite series of this form. The summation as n goes from 0 to infinity of a sub n times x to the n. This is called a power series. If it's centered at c, then we have the phrase x minus c captured throughout the series itself. We want to discuss, for the power series, are we able to find the so-called radius and the interval of convergence? The power series in x can be viewed here as a function of x. How are we able to extract from there the radius and the so-called interval of convergence? Well, let's examine that here, if you will. We talk about this value c, x minus c, where the so-called power series is centered. It's centered here at this value c. Here is c here. And we're looking for the radius. The radius can be examined in three terms. Here, the radius may be a single point, the radius may be an interval, and then the radius just may be the entire number line. So here, if the radius is a single point, we say that r is equal to 0. The radius is equal to 0. If the radius is on an interval, then we have something like x minus the center. The absolute value of that is less than some number r, the radius, where that interval looks like negative r less than x minus c is less than r. So that gives us negative r plus c less than x less than r plus c. Or if the radius is the entire number line, then we say that the radius, dealing with this, the radius is equal to infinity. So we have three particular cases. The radius could be centered at a point where there's no movement for the radius in terms of where convergence is. We're talking about where's the power series convergent? Well, the interval of convergence will tell us that. And the second possibility is that we do have an interval. And then here, the third possibility, the interval is the entire number line. So the convergence of a power series, what we said here, the series converges only at a point x equal to c. And so here we say that the radius is equal to 0. Or there exists some number r such that the series converges absolutely. Here, for this particular interval, it will diverge if the absolute value of x minus c is greater than r. Now, how do we get that? I'll let you know. I'll let you in on the secret in just a moment. The third possibility, the power series converges absolutely for all x, and here r is equal to infinity. If r is equal to infinity, then that means that the interval of convergence is from negative infinity to positive infinity. If we have convergence for a particular interval, then for a particular radius, then the interval is negative. Let's go back up here. Negative r plus c, comma r plus c. And there's always some work with that. So it's just not r plus c or negative r plus c. You have to do some algebra to definitely simplify. But this is the model. Recall two things from earlier in this chapter. One, the geometric series, and secondly, the ratio test. The objective, to find the interval of convergence for a power series. Secondly, to be able to solve a differential equation by power series representation. But here we're not going to solve a differential equation. But what we will do is to be able to determine the so-called interval of convergence. I save the differential equation part for the course differential equation. I think the key here is to be able to reduce the power series to its geometric series form, and I'll talk more about that in the next couple of sections. We don't need that here, and between now and when I post this PDF, you won't see that Part B disclaimer. That's for another course. I caught myself copying my notes from DE to this particular section because it's the same thing, but I need to modify that, and I will. So Part A, recall the geometric series. The geometric series, we said that is convergent to A divided by 1 minus R if R is bounded between 0 and 1. The absolute value of R is between 0 and 1. The geometric series, diverges when the absolute value of R is greater than 1. Now that's where, see if I have it highlighted here, you recall that for the power series to be convergent, there's going to be something less than, and then the power series to be divergent, it's going to be greater than 1. Let me tell you where that comes from. It comes from the so-called ratio test. So use the ratio test to find the interval of convergence. Well, here, just recall the actual ratio test. I'll just put it here. We said that the series converges absolutely when the limit of the absolute value of a sub n plus 1 divided by a sub n as n goes to infinity is less than 1. This is how we're going to build this guy. The absolute value of x minus c, the center, is less than r. We're going to build that based on the ratio test. And then for divergence, we build here that the absolute value of x minus c is greater than r. It comes directly from the ratio test. The ratio test, you recall, is inconclusive when the limit is equal to 1. And so here what I'm doing is just restating what I've restated and what I've restated. So there are three possibilities for the convergence. One that here, if there's divergence everywhere, the series converges at the center, whether you call it x equal to a or x equal to c. The radius is r equal to 0. If the radius is infinity, that means that the series converges everywhere, absolutely. And then part B, the series converges absolutely if the absolute value of x minus a is less than r. We have divergent series if the absolute value of x minus a is greater than r. Recall or remark, we haven't done it yet, so remark, when looking for the interval of convergence, you may be asked to check the endpoints, and we'll do that. Just graphically, what it looks like when the radius is 0, the convergence is only at the center. If the radius is infinity, that means convergence is everywhere. Or if you have an interval of convergence, then we've depicted that already before. Maybe I should take a pause here, and then we'll come back and look at some problems.